Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 12, Section 6, titled Tessellations. By the end of this video, you will have reviewed recent lessons on identifying transformations in tessellations, determining which figures will tessellate, and identifying symmetries in tessellations. If you'd like me to cover any of these topics in greater detail, please leave a request in the comment section below. Please subscribe to the channel if you find this video to be helpful. Thank you. Okay, let's start this review off with some definitions. First, a tessellation. A tessellation is a repeating pattern of figures that completely covers a plane without gaps or overlays. You can create tessellations with translations, rotations, and reflections. You can find tessellations in art, nature, and everyday life. Tiling is a tessellation. A tessellation is a tiling. Translational symmetry. A translation maps the tessellation onto itself. Glide reflectional symmetry. A glide reflection maps the tessellation onto itself. Objective 1. Identifying transformations in tessellations. A tessellation, or tiling, is a repeating pattern of figures that completely covers a plane without gaps or overlaps. You can create tessellations with translations, rotations, and reflections. You can find tessellations in art, which you can see example 1 below. There will be a picture of one of them. Nature, cells of a honeycomb, those are tessellations, and everyday life in a tiled floors. Okay. Okay, example 1, identifying the translation in a tessellation. So this is an art piece we've got going on here. It says identify a transformation and the repeating figure in this tessellation. Well, it says the arrow shows the translation. Well, here's the arrow right here, this arrow. Right here, this arrow is showing the translation. So what that's saying is if you take the goose or whatever, the swan or a goose or whatever this is, if you take the beak and you move it in this direction, you come back to another beak. And so this, when you slid this way, the entire picture came. And what is the repeated figure? The repeated figure is this goose. I guess we'll call it a goose, and the fish. And they're like married together here at this line right here, so that they go as a solid unit. And then you can move this, and if you do, you can translate it in many ways. You can translate this one diagonally this way. You can translate it this way along a line. You could go this way with it, and it'll repeat, but you're still going from beak to beak, no matter how you get there. If you go this way, you can do the same thing. It'll go this full, but you have to go that full distance to get it. But that is a repeating figure that you can move. You can't rotate it. You can only translate it. This is showing translations. If you rotate them, they won't fit. They'll only fit together in one orientation. So there's your translation. And that's the repeated figure. Here's the repeated figure over and over. Okay, example 1, check your understanding. It says identify a transformation and the repeated figure in each tessellation below. So what is the repeated figure, or what are we looking for here? You're going to go ahead and stop, think about this, and then when you come back, we can look a little more closely, okay? Okay, I'm sure you're back now. So let's see if we can figure this out. What is the repeated figure in this one on the right? And it appears in every case that the repeated figure is this fish. There's like a fish here, so it's got like, goes on here, here's the fish, right? Goes over here, and it goes up here, and then goes down here, and then it comes, oh, in fact, I should have went out here. I see it now. I skipped right by it. So it goes back up here, goes over here, comes down here, goes up and around, and then down here back. Okay, I think that is the fish. And here it's rotated. It's the same fish pointing in the other direction. Okay. There's the other, another, the same fish. Um, this is a pure rotation. There's translations. You can slide this far enough to where you're going to get from one. This is, let's see, in this particular pattern, as you see from here, this, the fish right here, the tail, this is the tail section. Well, we don't see the tail. Um, I want to find, okay, here's one right here. If we go from here, this is the back tail of this fish. The blue one, right? It slides, if we go from the tip of the tail, it goes all the way across over to here, to this point here. This is that same fish. So this is just, there's a red fish, a blue fish, and a yellow fish, and they're being oriented and, and turned and slid and rotated. So that's what we see in this picture. And then in the next picture, what is the, what do we have here? The, it wants to know what is the repeated figure and identify the transformation. Well, the transformation is a slide transformation where it slides from here to here, like goes from the horse's nose to here. So it can slide this way, it can slide down. It can, so each of these patterns here, we have the white and then we have a brown horse and rider, and here we have a white horse or yellow or whatever this off color is. It's not white, but anyway, so these are the patterns we have here. And you can take and you can grab this horse. It's so that the pattern is the double rider or double horse. One horse facing one way, the brown horse facing to the right, and the whiter, pale yellow horse facing to the left. And that is like the pair. And then they just keep repeating that over and over and over. You can't turn it upside down. It has to stay in that orientation. But that's the transformation and the repeating figures. Example 2, determining figures that will tessellate. Well, it says determine whether a regular 18-gon tessellates on a plane. Okay? Because the figure is is in a tessellations do not overlap or leave gaps, because the figures do not overlap or leave gaps, the sum of the measures of the angles around any vertex must be 360 degrees. So if you're rotating it in hunks of a circle, right, as you're going around, the hunks are going to eventually have to add up to 360 degrees. Otherwise, it didn't tessellate. If the angles around the vertex all are congruent, then the measure of each angle must be a factor of 360 degrees. So if it's literally a regular 18-gon, an 18-sided figure, then it's saying that A, the number A is the angle of the rotation, is found by 180 times the number of sides minus 2 divided by the number of sides. And so that's the regular formula for the measure of an angle of a regular polygon. So now you substitute 18 in for the n, and so you're going to get 180 times 18 minus 2 divided by 18, and you're going to get the angle is 660 degrees after you simplify it. Well, 160 is not a factor of 360. You cannot divide 160 into 360 evenly. It's 2 plus some odd amount. So the 18-gon will not tessellate. By the time you got back around to the full circle, you'd be coming up short, or eventually, to get rid of all gaps, you'd be overlapping. Okay, example 2, check your understanding. Explain why you can tessellate a plane with an equilateral triangle. So actually, the answer is right there for you already, isn't it? Why is it? Because the interior angles of an equilateral triangle are 60 degrees. 60, 60, 60 is 180. So each, right? And 60 divides into 360 evenly. So therefore, it will tessellate. I guess you could have used that formula too. We could have said 180 times 3 minus 2 divided by 3, and we would have come up with 60, and then we'd have divided 60 into 360. So objective 1B, identifying transformations in tessellations. It says, however, we should note that a figure does not need to be a regular polygon to tessellate. In the previous slides, we were looking at, an 18-gon or a triangle or whatever the polygon is, which was a regular polygon. They're telling you here it doesn't have to or need to be a regular polygon to tessellate. And you can look, theorem 12.6 says every triangle tessellates, every triangle, and you can see it. So here's our triangle, whatever, we don't know what this is, but it looks like a right angle, a right triangle of some type. I don't know what, maybe it's not right, maybe it's not quite a right triangle. But here's our triangle, right? Correct? Here's our triangle. And you can see that it tessellates, right? You can slide it from this point from here to here, and it repeats. And then you could also reflect it and slide it if you want, or not reflect it. Let's see. Yeah, you'd have to reflect it, I think, and then flip it. So the bottom line is it tessellates. And then every quadrilateral tessellates. So here's a quadrilateral. This they don't tessellate in every direction, by the way, but this one here you can see will flip and you can map it, right? So you can flip it down and map it. So this tessellates also. If you take this whole pattern here, well, let's try the bigger pattern. It'll be easier to see. This pattern right here. Okay. Here's this is a quadrilateral, but here's two quadrilaterals together. But the point is this shifts. You can take this now and shift it down to here and repeat the pattern. You would get this pattern repeated again and again and again. Objective 2, identifying symmetries in tessellations. A tessellation with regular hexagons at the right has reflectional symmetry in each of its blue lines and has rotational symmetry centered at each of the red points. The tessellation also has translational symmetry and glide symmetry, as shown below. But if you look at the pattern on the right, you see that every one of the little blue lines, if you could cut the entire figure. I'm just going to draw and want to see how good I can do here. You could draw this line right down through the center here, all the way here. And then you could take that pattern, and if you fold it along that line, those would all match up. They would actually, they would all flip right on top of the other ones, and they would be a mirror symmetry at this point. And you can do that on any one of those blue lines. You can do any one of the figures by themselves. It also has rotational symmetry, because you can rotate this around, and so it has translational symmetry. You can slide a pattern. You could take one of these patterns here, this one here, and you could slide it, this one, from here all the way over to here, right? And then you would end up being here on this one. Okay, so that's translational symmetry we're talking about there. This actually shows you translational symmetry. Translational maps a tessellation onto itself, and this is it right here. This is the picture right here, what we just drew. That's translational symmetry. I'll draw it again from here to here. That would be the full move, and then you'd have this piece here. You could look at this. These pieces are together, right? You could do this. Every one of these pieces. It's the same thing here. Here's another one. Same thing. There's loads of symmetry in this tessellation. Okay, and you see you can move over one and shift it up a bit, and then you have the same thing again. This is nice stuff. Glide reflection symmetry. That shows that you can take any one of these and you can take the whole section. You could take this whole section, let's say about this line here. Let me change, maybe let me change colors maybe. If you went, what did I do? Did I do this one? Blue, blue up here like this. You do that right along those lines. And you could slide the whole pattern up. You could take the entire piece and slide it up 1, 2, 10, however many um, figures you wanted to. Glide reflection shows that you're going sliding the pieces or multiple pieces as a group in the same direction. You have that's all translational. Translational symmetry shows just like the same, basically the same thing. Those are getting mapped onto themselves. Okay, example 3, identifying symmetries and tessellations. List the symmetries in the tessellation. So what are the symmetries that we have in this particular these particular translations and tessellations, excuse me. Well, we can see that we have rotational, right? So we see all these triangles. Every triangle, I'll just draw on one of them here. Every one of these triangles can translate, it can slide, right? It can do this, right? Each one of these can do the same slide. We can slide this one from here to here, right? They all slide. These little ones do the same things. From this little one here to this little one here. From this little triangle right here to this little triangle right here. It could be, okay, there's translation here. So we have translational symmetry, and they're showing it right here on the right. The blue line, which I'm covering in red, the blue line, I'll go ahead and erase that. I'll go back and do that in blue. Okay. So the blue line, let me leave it in blue, right? The blue line right here. Now I get to draw on it now. That is translational symmetry. You move it and it's repeating. Okay. That goes in more than just one. It goes in every direction. You can pretty much find a match for these if you go far enough for sure. And then there's rotational symmetry around the red points. So every one of these triangles, now we'll go back to red. Come on, red. There you are. So if you go to this point here, this triangle can rotate 3 times, right? We know that there are 3 rotations, 120 degrees each around this circle, around the triangle, right? We can do the same thing on the smaller triangle right here. You can do it on this little teeny triangle right down in here. They all have rotational symmetry, and they also have translational, because you can take this one here and you can slide it over to here. Okay, you can take any one of these and move them. This one here can be slid to here. But they always have to be in the same orientation and one of the three 120 degrees angles on the rotation. Okay, example 3, check your understanding. List the symmetries in the tessellation at the right. So go ahead and stop it and look at it for a while and see which ones you can come up with. When you come back, we'll do it together. Okay, now that you've had time to do that, let's see what ones we can find. So first of all, there's not that easy to see. However, there is line symmetry, and I'm going to see if I can pick one out of here. If we were to take and go through, but I guess they're on an angle. So they're not like the mask. Remember in the beginning of the chapter, the mask that we could see had the beautiful vertical line down. I don't think we're going to find that as easily. But if we did this, let's see, if we're going, the angle is this way. I think I want to draw it. They're hard to spot. Okay, let's just do this. If I went here it's hard to see, but I went down here. Oops, like that. Let me, I gotta change my angle of my hand maybe to this guy, then through here, and then from this guy down here to here, here, and out here. Um, you can see that if you fold this, you can fold it right in half, and you'll get, if you fold it along this line, this piece right here, right there, I'm going to change colors, would match this piece right here. Oh, did I? Let's see. Yeah, that piece, and then I'm out here getting this one. They're hard to see. And then I get this one. Oh, I lost track of where I started. So I said we're going to get this piece right here. Out right here. Here it goes. This one right here. This piece right here. And the red piece. These things sneak up on you, and you can't. You lose track of them. Okay. So we cut it down the center, and the next one, if you cut this one, look, this one goes up here, cuts this one in half, but it's the same thing. Okay. So now, so that's talking about this one here. So I'll go here, here, and here. Okay, you get the picture. So there's line symmetry. There's translational symmetry where we can take like this whole figure right here, and you can slide it all the way over. You can go to this one here. This pattern here is the same as this pattern here, right? As the same as this one over here. So they're just duplicates of each other. You can slide this up vertical. You can take all of these patterns. You can take all of these and you can grab every one of them together and slide them up. You can glide them into an upper position or down or from right to left. You can do that on all of them. They're rotational. So you have rotational. So what did we have? We had line. We had translational. What else did we have? We have rotational because this thing will switch. If you take about this is the center point, you can rotate this all the way around over here and it'll be the same if you go back to this side. You can rotate that all the way around. This point comes over here to become this point. The center right here ends up at the center over here when you rotate it around this point. So it's rotational. Rotational symmetry. There's translational. We talked about that, how you can take the whole piece and slide it. You can take individual pieces in here and slide each little one. You can take this piece right here, and you can move it to this side to right here. So I'll just color that one in. You can color, take this one and slide it to the little piece. They're all, let's see, what else do we have? I see, well, reflectional, we already did the line symmetry. I see reflectional symmetry. It's in there. Well, I think that's pretty close to what I've line, translational, reflectional, reflection, right? Reflectional, line, rotation, glide. Is glide in here? Glide, glide. I think it's, those are mostly the ones I can see. Okay, good job.